Dear participants of the first international workshop on bioinformatics and applied information technologies, I would like to present the results of research on the topic Smart Prosthetics in Surgery, Artificial Intelligence-Driven Tactile Feedback using Piezoelectric Sensors. Nowadays, artificial intelligence is revolutionizing nearly every aspect of modern life. In the medical field, robotic surgery is the sector with some of the most innovative and impactful advancement. At the heart of this evolution is the robotic human hand, which emulates the dexterity and versatility of its biological counterpart. One of the key technologies driving this precision is the integration of higher performance micromotors, which enable fine control and articulation necessary for various surgical tasks. Achieving artificial tactility is one of the challenges in the fields of smart robotics and artificial intelligence because touch emulation relies on high performance pressure sensor array, signal reading, information processing, and feedback control. However, an equally critical aspect of robotic surgery is the ability to provide surgeons with realistic sense of touch, haptic feedback. This tactile feedback is essential for enhancing the surgeon's ability to manipulate delicate tissues, apply appropriate pressure, and avoid unintended damage. There are two primary control methods which are used nowadays in modern robotic surgery. Semi-automatic systems rely on the telemanipulator, where the surgeon directly controls the robotic arms through joysticks or control consoles. In such setup, tactile sensors like piezoelectric transducers play a vital role in transmitting force feedback to the console, allowing the surgeon to feel the resistance or textile of the tissue being handled. On the other hand, automatic control systems which focus on repetitive surgical tasks also benefit from sensor feedback to ensure consistency and safety during operations. The integration of high performance micromotors and tactile sensor is transforming the landscape of robotic surgery. The main types of sensors for tactile feedback include capacitive, resistive, optical, force moment, and piezo sensors. Capacitive sensors are used to detect changes in capacitance upon contact with an object. They are well suited for creating a light touch sensation and can detect various pressures. Their advantages include higher sensitivity to small changes and a wide range of applications. Resistive sensors change their resistance in response to pressure. Their primary disadvantage for tactile sensation is the wear and tear of the sensor materials over time and their lower sensitivity to small changes compared to capacitive sensors. Optical sensors measure changes in light intensity when in contact with an object. They can be used to monitor deformation and finger movements in prosthetics. However, their complexity in integration into compact systems and higher cost limit their use in prosthetics. Force moment sensors are used to measure multidimensional force and movements, particularly useful in surgical systems for precise pressure and motor control. Their advantages include the ability to measure complex multidimensional forces and provide higher precision control of instruments. The main disadvantages are their higher cost and complexity in setup. Piezoelectric sensors are a type of sensors that use the piezoelectric effect to measure mechanical changes such as pressure, force, acceleration, etc. The basic principle of operation of piezoelectric sensors is based on the property of certain materials to generate an electrical change in response to mechanical impact. This makes them ideal for use in various systems, including prosthetics, where it's important to obtain accurate data on tactile interactions. The concept of using piezoelectric sensors to create tactile sensation is in the prosthetic hand is promising, as they can effectively measure mechanical pressure and vibrations. Piezoelectric sensors are capable of converting mechanical energy into electrical signals, making them ideal for systems that need to sense physical contacts. To generate more realistic tactile feedback, piezoelectric sensors can be combined with another sensors. The integration of piezoelectric sensors into prosthetics for surgical systems is an innovative approach to provide tactile feedback during operations. One of the simplest ways to integrate piezoelectric sensors is by installing them in the fingers of robotic hand or prosthetic. The sensors can be placed on each finger joint or on the fingertips to sense pressure. They detect the deformation or force applied to the fingers and transmit this data to the feedback system. For maximum accuracy, piezoelectric sensors can be combined with another sensors, for example temperature sensor, to provide a full range of tactile sensation. Moreover, transferring these tactile data patterns through cloud-based services adds another layer of innovation. It facilitates the centralization of tactile information, enabling real-time processing, sharing, and feedback across different devices or locations. For example, a surgeon in one part of the world could receive tactile feedback from a robotic arm operating remotely, significantly expanding the possibilities for telemedicine and remote surgery. By leveraging artificial intelligence and cloud-based learning systems, this approach not only brings precision and personalization, but also holds the potential for global knowledge sharing. Surgeons worldwide could contribute to and benefit from an ever-expanding database of tactile patterns, democratizing access to cutting-edge surgical tools and making high-quality tactile feedback systems widely available in various healthcare settings. There are a few requirements. Firstly, piezoelectric sensors in real time detect various mechanical changes such as force, vibration. Based on the signals obtained from piezoelectric sensors, a database of different tactile patterns can be created, corresponding to various types of physical integrations, soft or hard tissues, or tool grips. The collected patterns are stored in cloud services for further analysis and optimization, and the data stored in the cloud can be transmitted through the control interface to the surgeon, and cloud technology enable the processing and analysis of large amount of data, creating the potential for forming realistic and accurate tactile sensation for surgeon. And short summary: the use of piezo sensors helps surgeons to feel real-time contact with tissues, thereby improving control during surgeries. Interacting of artificial intelligence allows the dynamic adjustment of feedback and optimizes interaction with tools and tissues. Multisensory systems help greatly enhance the quality and effectiveness of surgical procedures. And finally, cloud technology facilitates the collection, analysis, and storage of large amount of tactile data, improving the accuracy of feedback. Thank you very much for your attention.